Okay, so what did we learn last time? We learned several definitions like weight. What is a weight? And weight vector. So we denoted, say, mu, v, and we learned weight space and multiplicity, and what else? Root and root vector. They are all for SL3C. What is a weight? What is the definition of a weight? So weight, we have to say representation for representation pi, right? Also, for these weights, we have to say for representations, but these are definitions only using SL3. So this weight is, in other words, simultaneous eigenvector values. Weight vector, simultaneous eigenvector, weight space, it's a kind of eigenspace, space of weight vectors. Multiplicity is the dimension of the weight space. And what is the root? So weight for the adjoint representations. Weight for the adjoint representation. And this is weight vector for the adjoint representation. Okay? And using this, we will develop a theory of representations for SL3. All right, so section 6.3, the theorem of the highest weight. So for SL2 case, every representation is determined by its largest eigenvalue. And similarly, for SL3, there will be some kind of weight, highest weight, that determines the irreducible representation. So let's say pi is a representation of SL3C acting on a vector space V. And mu is a weight, so simultaneous eigenvector. Eigenvector for H1 and H2. Okay? So we have basis. So here, if you recall, we have basis like H1, H2, and X1, X2, X3, Y1, Y2, Y3. So simultaneous eigenvalue for H1, H2, or more precisely, pi of H1 and pi of H2. So it's a weight with weight vector, say V. Then we showed that for each root, Z alpha, and we know that this must be one of these. So these are the root vectors. Okay, X1, X2, X3, Y1, Y2, Y3. So these are all the root vectors. So for each root vector with root alpha, we know that pi of, if you apply this root vector to the weight vector V, then we know that this is either 0 or another root vector, or another weight vector with weight what? Mu plus alpha. Okay? Do you remember? We learned this last time. And so we are working with a finite dimensional vector space. So since dimension of V is finite, we eventually get 0 if we apply root vectors repeatedly, right? So we apply say x1 and then we apply x2 or x2 well, we can keep just applying root vectors to this weight. Then eventually we must get 0 because we cannot have like infinitely many different root vectors or different weights. Okay, so here's a definition. So, and we selected these special root vectors, and they are called positive simple roots, or just simply simple roots. Then other roots will be a linear combination of this with all non-negative integer coefficients or all non-positive integer coefficients. And let's say we have two weights, so weights of a representation, say pi. And we say that mu1 is higher than mu2 and denoted mu1 higher than mu2. So this is the definition. If mu1 minus mu2 is a linear combination of alpha and beta with non-negative real number coefficient, A, B, this, like that. Okay? So this, now we have a partial order on the weights. So notice that this is a partial order, it's not a total order. Sometimes we may not have this, okay? Now also notice that A, B are not necessarily integers. They could be rational or real, usually rational, but they have to be rational. But anyway, they may not be real integers. And if and mu0 is called a highest weight for a representation, given representation pi, if it is higher than every weight in pi. Mu0 is greater than or equal to mu for all weight mu of pi. Okay? If this happens, then highest weight. So from this definition, it's not. We may not have. There may not be any highest weight because this is not a total order. So just only a partial order. Okay. So this is a partial order. All right. Let me give you some example. So, note. Yeah, I already mentioned. Actually, the textbook is written like curvy inequality, but it's a little difficult to write, so I will simply write like that. So this is a partial order on the weights, on the set of all weights. And for example, and we can also talk about 0. So for instance, alpha minus alpha 2 is not higher than 0 because yeah, if you take the difference of them, like 0 is of course alpha 1 minus alpha 2, the coefficients are not real number, not positive, non-negative, so no. Okay. And also, this is not smaller than or lower than 0, because again 0 minus alpha 1 minus alpha 2, which is minus alpha 1 plus alpha 2, the coefficients are not positive. So it's not a partial order. We cannot compare these two weights. Okay? And also, it's possible that these A, B are not integers. For example, 0, 1, this can be a weight of some representation. This is higher than 0, 0 because 1, 0 minus 0, 0 is of course 1, 0. It is 2 over 3 alpha 1 plus 1/3 alpha 2. So coefficients are non-integers. Okay, now this is a theorem that we want to prove. Theorem of highest weight. It's a very important theorem. It has several parts. First, every irreducible representation of SL3 is the direct sum of its weight spaces. So here, a direct sum as a vector space. So usually, a weight space is not an invariant space. So it's not a direct sum as representations, just a direct sum as a vector space. Okay. And second, every irreducible representation of this, I will just omit this, has, so everything is for SL3C. I will simply omit this. Every irreducible representation has a unique highest weight mu. Third, two irreducible representations with the same highest weight. I'm going to write it just this way. Highest weight are isomorphic. In other words, an irreducible representation is determined by its highest weight. Just like irreducible representation for SL2 is determined by its largest eigenvalue. 4. The highest weight mu of an irreducible representation is of this form. M1, M2. Okay. Let's write this way. Non-negative integers. So M1 and M2 must be non-negative integers. Just like the highest eigenvalue or largest eigenvalue for SL2, irreducible representation of SL2 is a non-negative integer. Fifth, finally, and conversely, for every such pair, M1, M2, pair of non-negative integers, there is an irreducible representation whose weight is this. There exists, of course, the unique up to isomorphism by 4. There is an irreducible representation with highest weight M1, M2. So here is the 5 statements for this theorem. So this is kind of a parallel theorem for the results that we learned for SL2. right? Everything is like generalized nicely this way. So today we'll prove this, and proof consists of several propositions. So we will prove many propositions today. Any question before I move on? Okay. So the next section is the proof of the theorem. So first I'm going to now give you some proposition numbers, the same as in the textbook, because we will refer to this proposition pi. This is an irreducible representation of SL3C. Okay, from now on, I'm going to just omit this. Everything is a representation of this. Okay, if I don't say anything, then pi h1, pi h2, this can be simultaneously diagonalized. I.e., in other words, V is the direct sum of, let me write this way. So, direct sum of weight spaces. So this means the weight space corresponding to the weight mu. So these two sentences, they mean exactly the same thing. Yeah, I explained this last time. So we want to show this. The direct sum as a direct sum of the weight spaces. So first, so let W be the subspace of V in our representation, spanned by all the weight vectors. So first we will show that the weight vectors span the whole space, and then we will show that it is a direct sum. So claim is that W is not just a subspace, but is the whole space. But we already know that there is at least one weight. We proved this last time. Okay? We proved that V has at least one weight vector. So W is not 0. We know this. And since V is irreducible, it is sufficient to show that this is an invariant subspace. Sufficient to show that W is invariant. Because irreducible means if there is an invariant subspace, it must be 0 or itself. So because we know that it's non-zero, must be V. All right. So, but what is the meaning of this? V is invariant. That means if you apply every basis element of SL3 to it, then it will stay just there. It will never leave this space. That's what invariant subspace means. So to do that, let's consider one vector. But this means this is a weight vector with weight. Oh, actually, no. It's technically what I said was wrong. This is not a weight vector, but it is enough to consider only the weight vectors because W is spanned by weight vectors. So if you have two different weight vectors, if you add them together, this may not be a weight vector. But that's okay, because if you can only prove this for weight vectors, then it will be sufficient, because they will span this. Okay? If you prove this for bases, then this is good. So let's say we have a weight vector with weight mu. And okay, since let's consider any root vector. So x1, x2, basically we have to consider all basis elements of SL3, but we don't really need H1 or H2. That's kind of trivial. What happens if you apply H1 here? It will be just a constant multiple of V or W, right? Because this is a weight vector. If you apply H2, it's just the same up to a scalar. So we only need to worry about this, because H1, H2 is the same vector up to scalar. So we will show that Z, we will see what happens to this. What is this? This is a root vector with some root, say alpha, we can say that. For any of this, it is a root vector, we know that. Let's write alpha here just to indicate that it's a root vector with root alpha. Then this is either 0 or root vector, another root vector with weight with root mu plus alpha. That means if you apply any basis element, it will be 0 or another element which is a root weight. That means this is always in W. So invariant. That's the proof of the claim. Is this okay? Now we have to show that it is a direct sum. We only showed that, so this claim only means that V is, say, let's say sigma, only a sum like mu1. If mu1, mu2 are not necessarily direct just yet, but eventually it will be a direct sum. We want to show that. Okay, so how can we show that? But this will follow from the facts that I'm going to tell you in the next slide page. This direct sum follows from the fact, say below, which I'm going to explain now. Okay, so what is the fact? So fact, this is in fact proposition A.17. I'm not going to prove it. Let's say V is a vector space. A1. So the statement is a little more general than what we are doing. Operators on V, meaning linear transformation from V to V. Mu1 dot 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 mu m, distinct weight for A1 dot 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 AK. Okay, we defined weight only for representations, but here there is no representation. So what does this mean then? Distinct weight. This simply means simultaneous eigenvectors. So it means simultaneous eigenvalues, sorry. Okay? Just like the usual weight. Or i.e. something like mu is something like m. Yeah, this m is different from this m1 dot 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 mk, where a1 v equals, there exists a vector v, simultaneous eigenvector m1 v, a2 v equals m2 v, etc. This is what I mean by this weight. All right? So here is the definition of the weight for operators. Okay, then let's say v1, vm, so vectors in the corresponding weight spaces. Okay. So this is a weight vector corresponding to this weight. So just like this. So v is a weight vector for this mu, something like that. And statement is the following: if v1, if their sum is 0, then they all have to be 0. And basically this means the weight spaces, they form a direct sum. So weight space is a direct sum. So the sum of weight spaces is direct. Okay. This is what that means. Oh, this is statement 1. But for this here, it follows from 1, fact 1. Because we have weight, there must be 0. There must be a direct sum. Okay? This is done. And the second statement of this fact is that if mu1 plus dot dot dot, if this is a weight, vector with weight mu. Oh, by the way, this is all distinct weight. Then this must be mu must be one of these, mu j, and mu I, v I equals 0 for all I. Oh, I don't think we need this. Yeah, I think it's true in general. Yeah. So what is the meaning of 2? Yeah, I kind of briefly mentioned earlier. If you have two different weight vectors with different weights, if you add them, that's not going to be a weight. So because if you want to make a weight out by adding weight vectors, there's only one part surviving. The other must be 0. Okay? This means the weight must be one of the weights there, and the other vectors must be 0. This is the statement. Or in other words, this means if you can write a vector space as a direct sum of weight spaces, and if V is a weight vector, then V is in one of the components for some mu. So weight cannot be obtained by adding two different weight vectors. Must be only from one component. That's vector 2, fact 2. So we will use this. We have already used this, but this will be used later. Okay. All right. So the first proposition we proved is this. We can simultaneously diagonalize every irreducible representation. Okay, so the next step, we need to define something. This is also a very important definition. The partial order is also very important. Everything today is very important, basically. Our representation of SL3, of course, is called the highest weight cyclic representation. So highest weight cyclic representation with weight with highest weight mu, which is of course m1, m2, if the following condition holds. If there exists a non-zero vector in our space such that first V is a weight vector with weight mu. So it's a highest weight vector. Second, if we apply x, any x sub j, to 0, it's going to be 0. To v, it's going to be 0 for all j 1 to 3. Third, the smallest invariant subspace of V containing this vector V is the whole space V. So here is the definition of highest weight cyclic. So usually when we say something is cyclic, that means, so if you remember for in your undergraduate algebra, what is a cyclic group? It's a group generated by one element, right? So cyclic means generated by one element. If something can be generated by one element, usually it's called a cyclic. So here it is generated by one element. But what does that mean? Something is generated by one element. For a group, for a cyclic group, we have one generator. That means every element in this group is the power of this element. But in general, we don't really have power of something. But cyclic means this. This means cyclic. This is cyclic. This is the cyclic condition. The smallest invariance of space containing V is V. So generated by something means the smallest space containing those elements. Okay? The cyclic condition. And this means a weight vector. It has a weight vector corresponding to this weight. And this corresponds to the highest weight. So second condition means highest weight. Third condition means cyclic. So we call this highest weight cyclic. This will be a very important concept because it turns out that every irreducible representation is like this. Okay, so in order to proceed, we are going to need this lemma. I guess I'm going to use the next page. So lemma is called reordering lemma. This is very useful and interesting lemma, and it's true for any Lie algebra. So let's say G is any Lie algebra, and pi is a representation of G. And x1 ... xm, this is on ordered basis for G here as a vector space. So Lie algebra is a vector space, so we have a basis. Ordered basis means basis, but we just give them some order. The first element in our basis is this, the second one is this, etc. Because the order will be important. Then, any expression J1, J2, Jn can be expressed as a linear sum of things like this. Where these k's are non-negative integers and their sum is less than or equal to n. We're going to call this a star condition or star expression. Okay, so what is the meaning of this? Our Lie algebra is non-commutative, usually. If it's commutative, it's still a Lie algebra, but it's very simple. If this is commutative, then this is clear. This is clearly true. Because it's non-commutative, we cannot rearrange this any order we want. But if G is commutative, let's think about that case. This is trivial because we can always order this as we wish, because xy is yx. But that's not true in general, so this is a not trivial statement. But the thing is, this can always be written in terms of this. But notice that this is not equal to just not a single term of this form. Or rather, the theorem is saying that this is a sum of things like this. That's what this theorem is saying. Okay? Or lemma. This is useful. And here, how many terms do we have? Or factors? We have n factors, capital N. And here we have, for each term, we have at most n factors. So we may have fewer factors in our term. But we may have many terms, but they all have fewer factors than this. Okay, so let's prove this. It's going to be an induction on n. What happens if n equals 1? We have only one factor. Can you write this as a linear sum of these? Yes, it's clear. It's already in this form. Is that right? It's already in this form. Exactly one of these is 1 and the others are 0. So it's already in this form, so there's nothing to prove. So assume that's true for n, and consider, as usual in this induction step, now we are considering n plus 1 case. And we assume that everything less than n plus 1 is true. Okay, so by induction hypothesis, so basically now we have one more term. Let's write this way. Now n equals, now is n plus, we have n plus 1 factors like that. But we can use induction to the last n factors. From this is going to be a sum of things like this, okay, of this form. They are already in this order. But we have to multiply this at the left. So it's sufficient to show, if you look at each factor here. So let's now consider just one. Now star, what is star? This is sum of things in star. Okay? Then in this sum, everything we can work with every term, and then every term will be expressed as sum of these stars. So at the end, everything is a sum of stars. Okay? But how can we do that? If this is commutative, you can just simply move this to this right position. There's nothing seriously difficult, but it is not commutative, so we cannot really exchange these two consecutive factors. However, we can somehow exchange this by adding some more terms using this property. So strategy, idea is simple. Idea. Move this to its right position, correct position. Maybe somewhere here between xj1 plus 1 and xj1. Let's say just x1. Let's say x. It doesn't really matter which index we say, right? So let's say j1 equals j, just to avoid any complicated subscript. So we want to move this into the jth position. How can you do that? We have this property xl. This is not equal to this, but it is equal to something else. Plus we know this. Why? Because pi is a representation. So pi is a representation. So we have something like pi xy equals pi x pi y, but the bracket here is the commutator. So if you rewrite this, you will obtain this. So the idea is here, rewrite this as the reverse of this plus one more term. But this now, what happens? You can write this as a sum of ordered basis, xj something, or xj prime, I don't know, something like that. But then we have only n factors. We can use the induction hypothesis to write this as sum of this. Okay? And for this, we have to move this again and again, again, again. But each time we switch to the order of two consecutive factors, we have to introduce more term, one more term. But the term, if you introduce this, we have one fewer factor. So by induction hypothesis, that can be dealt with. So eventually, everything will be in this form. That's basically the idea. I'm not going to write the full details. So that's the proof, basically. Now, the full detail can be found in, you can read. That's the idea. Okay, so this is going to be very useful for us. Okay, any question about the proof? So, proposition 6.11. Suppose we have highest weight cyclic representation of SL3 with weight mu, highest weight mu. Then first pi has highest weight mu. That sounds a little strange. Okay, I think I have to say, I have to define this way. So, where is it? With just weight. Let's say just weight. I'm not in this definition. With weight. I'm not saying that it's going to be a highest weight, because highest weight means it is greater than every weight for all weight sigma. But I'm not saying that in this definition. Eventually it's going to be true, but that's something we want to show. So this will be used to show that mu is a highest weight. So for now, mu is just some weight. We don't know whether this is highest weight. Okay? So yeah, that was what I wrote here is wrong. I mean, as a definition, it should be just weight. So we want to show that that's in fact highest weight. Okay. So second, the weight space for mu has dimension 1. Oh, by the way, so this means as in the definition of highest weight cyclic. Not just any weight, of course. So weight that satisfies the conditions in our definition of highest weight. Like if you apply x1, x2, x3 to this weight vector, it's going to be 0 and things like that. All right. So proof. Let's say V is a vector. Satisfying the conditions in the definition. Highest weight cyclic. Let's go back to the definition. So right there. So this vector, V. Take that vector. There exists vector V such that this is a weight vector with weight mu, and if you apply x to it, it's going to be 0, and the smallest invariant space containing V is the whole space. So we assume that. And let W be the span of vectors of the form in this form, W equals pi yj1 pi yjn. Every vector that can be obtained from V by applying y's. Okay? Just define W, a vector space like that, and then we want to show something. Claim W is invariant subspace. So it's just a vector space for now, but it turns out that it's an invariant subspace. How can you show that? So enough to show so again, to show that some vector space is invariant, it's enough to show that if you apply any basis element of SL3, it stays there. In other words, this is inside W. For all Z like xi, yi, and hi. Hi is for 1, 2. Here we have 2 indices, 3 indices, okay? But is that true? Or equivalently, first pi xi, but every basis element here must be of this form. Is it enough to show that if you apply pi xi to one of these, then it's still in this form, or some of those? For all I from 1 to 3, right? If you apply x to it, stay there, because it's a basis element. And also, if you apply y, must be there. And if you apply h, must be there, right? But here for h, I is from 1 to 2. There is no h3. All right? We want to show that this is a linear sum of this. Okay, which one is easiest among 1 to 3? Which one is easiest, do you think? 2? 3? Everything is difficult? One of these is trivial. Which one is that? One? 2? Okay, let's vote for fun. I think 1 is easiest. Okay. 2 is easiest. Okay, 3. Okay. Why do you think 1 is easiest? They are all easy. After all, they are all easy, but 2 is the easiest, right? Because it is already in this form, right? These are, we applied y's and then we applied y again. It is already in this form, so it's trivial, right? How can this 1 easier than 2 or 3? So it's the easiest. It's a trivial. But for 1 and 3, we have to use the reordering lemma. For 1 and 3, by reordering lemma. So we want to move this thing over here all the way to the front. Can you do that? We can order, let's order the basis. This is not just a basis, but we can give an order to it. How do you want to order this if you want to use the ordered basis? Let's order the basis for the standard basis, of course, in this way. Let's look at that. So here, oh no, we want to have y's on the left, right? That's what we want to know. That's what we want to do. So let's order in this way. Y1, among 1, the indices doesn't matter. Let's order in this way. H1, H2, X1, X2, X3. Okay? Let's order the basis like that. This is going to be important. Now, using the reordering lemma to the first, this is the, I think I wrote this backward. Yeah, sorry about that. This is going to be X, 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 and Y, Y, and Y. Because we want Y to the end, or the left side is the end. We apply from right to left. By reordering lemma, 1 can be rewritten in this way. Pi y something. I'm not going to write down the specific indices. xi, like that. Or to be very, very specific, I think it should be sum of something, some coefficient y3 something, y2 something, y1 something, h1 something, h2 something, x1 something, x2, x3, finally v. Okay? Everything will be of this form, or 1 or 2, or 1, 2, 3 all together. They all can be written in this way by the reordering lemma. Okay? But now what happens if one of these is non-zero? If you apply one of the x's to v, it's going to be a 0 because of the definition in the highest weight. So if these are non-zero, it will be 0. The term will vanish. So we may assume that these are all, we don't have this term. Because if there is, the vector will be will be annihilated. What about this now? Again, we can ignore this because this is a weight vector. So if you apply h's, it will be just a constant multiple. So again, it will be just v times constant multiple, so we can ignore this. But then finally, it will be just sum of this form. So it will be in W. That's the proof of this claim. So it's an invariant subspace. Right. But this means V is W. Why? We didn't say that V is an invariant, V is irreducible. We didn't say that, but how can we say that V is equal to W? Because from the definition of the highest way cyclic, V is the smallest invariant subspace containing V. But this does have a V, and it is invariant, so it must be the whole space. So, cyclic condition. Okay, so what do we need to show? So the first one is done, right? No, it's not done. We will prove 1 and 2 at the same time by applying. So let's consider what happens if we apply y. If we have v, the weight is v and mu. The weight for v is mu. But if you apply any of y's, the weight will be mu minus alpha 1 or alpha 2 or alpha 1 minus alpha 2, etc. So if we apply y's there, the weight will get lower. Is that right? Is that right? If we apply yi, like, then it's a weight vector with weight mu plus alpha 1 or alpha 2 or alpha 1 plus alpha 2. Oh, sorry, minus. If you apply y, the weight will be minus alpha 1, alpha 2, alpha 2. If you apply one more, like a j, if you apply one more, we only get more minus alphas, alpha 1, alpha 2. So it always get lower. So we always get weight lower is the opposite word for the higher, lower than mu. This is lower than mu, this is lower than mu, right? This is lower than mu. If you ever apply one single y, it will be small, the weight will be smaller. This means mu, but every weight vector will be of this form. So mu is highest is a highest weight. Everything else will be smaller than mu. Okay? And also, the dimension of the weight space corresponding to mu is 1 because V is the only weight vector with weight mu. So that's the end of the proof. Okay. So the next proposition is this. Now let's say it's an irreducible representation of SL3. Then pi is a highest weight cyclic representation with a unique highest weight, say mu. So in other words, every representation is a highest rate representation, cyclic representation. All right, let's see how we can prove this. So first of all, V is a finite dimensional. We only consider finite dimensional representation. This means there are only finitely many weights. So this representation has only finitely many weights. What can you say there from there? From there, we can say that there exists a maximal weight mu with, say, weight vector okay. So what does this mean? So usually in mathematics we distinguish these two words, maximal and maximum. Maximal and maximum are different usually. So maximum is maximal, but the converse is not true. So because we are working with partial order, maximum means something that is bigger than everything. So like highest weight. But maximal means something that has nothing above it. So for instance, if you know Hasse diagram, so something is above, then it's bigger than this. This is maximal, but not maximum. Because this is not bigger than this, but there's nothing that's bigger than this, so it's maximal. But when we have a finite post set, then there is always a maximal element. That's true. If you have a post set like this, finite order, then there is always a maximal element. All right, so, but we don't know yet whether this is the highest weight because it's only maximal. So here maximal means mu maximal means that there is no weight, say lambda, such that lambda bigger than mu. This is what maximal means in our order, partial order. And we know that since mu plus alpha 1, mu plus alpha 2, mu plus alpha 1 plus alpha 2 are higher than mu, right? This minus this is a positive sum of alpha 1, alpha 2. This means these are not weight. This cannot be weight because otherwise this is not a maximal element. Okay? These are not weights. That means if we apply xi to, but this is the root, and the corresponding root vector is x1. So if we apply x1 for any I, it's going to be 0 for all I 1 to 3. Because if you apply, if it's non-zero, then this will be a weight vector with weight this. But this cannot be a weight, so it's going to be 0. Also for this, 0. Also for this, 0. It's x3. And V is irreducible. That means smallest invariant subspace containing V is what? Must be V, because otherwise it's not going to be invariant subspace, irreducible. So V satisfies all the conditions for the highest weight cyclic with weight mu. That's the proof. Okay, let's do one or two more propositions. But first we will accept this fact. Every finite dimensional representation of SL3 is completely reducible. This means V is always a direct sum of irreducibles. That's what this completely reducible means. This can be proved, but we're not going to do that, and we'll just accept this fact. So from now on, every representation of SL3 will be finitely reducible. So it's a representation of SL3 that is highest weight and cyclic. And then it must be irreducible. So it's kind of the converse of the previous proposition. Proof. We know that highest weight cyclic representation has a highest weight and highest weight vector. So let mu be the highest weight with a weight vector V. All right? And because this is completely reducible, we can write things like that. So let's decompose this into irreducibles. So every sum end here is irreducible. So it's an irreducible representation now. But we know from proposition 6.19, every irreducible representation is a direct sum of its weight spaces. So let's say rho. Let's write this way. So notation is a little strange, but so it's a direct sum of weight spaces. We prove this for irreducibles. So it's a corresponding weight. So this is weight space with weight rho. And since mu is a weight, and as a vector space, V is what? Sum of J and rho and something like this. Some weight spaces like that. So V is also a weight spaces. So V is also a direct sum of weight spaces, right? If you combine them together. But then, so V rho, this is direct sum, like that. And by the fact that I showed you earlier, mu must be one of the mu must be exactly one of these row. You cannot combine two weights to get a new one. So mu this is non-zero for some for some j. So in particular, mu is one of the summands here. Only one summand. Mu belongs or v, this v vector, weight vector v belongs to one of these summands. And if we have that, then one of these must be non-zero, so we can say this. All right? But then, what's next? That means this Vj has a weight vector with weight mu. All right? So Vj has a weight vector with weight mu. But highest weight cyclic, for highest weight cyclic representation with highest weight mu, what is the dimension of the weight space corresponding to mu? It's 1. So since dimension of the weight space corresponding to mu is 1, V is the only weight vector with weight mu. We know this. And Vj contains such a weight vector. That means V must be in Vj. Okay? And Vj is invariant subspace containing V. That means V must be Vj. Because of the highest weight cyclic condition. But then that means we have only one summand, so V is irreducible. That's the proof. Is everything okay? Yeah, probably you want to go back to your home and then read the textbook and then review what we learned. So like I said earlier, the materials that we learned this week will be very important, so try to review them after the lecture. Okay, I will stop here and thank you for your attention.